Hello everyone, thank you for joining. Today I present Advanced Student Project Design and Prototype of a Dynamic Wireless Power Transfer System for Electric Vehicle at 85 kHz using LCC-C compensation topology. My name is Ahmad Hisham Kamil and my teammate is Devani Putri Firdausi. Our advisor is Professor Sung Lin Lee. This is our project and our team. Next is the overview. Here is today's outline, background, which is background, research motivation, circuit architecture, waveforms, expected results, and simulation. Also numerical measurements and conclusions. I will start with the background and motivation. The global shift toward electric vehicles or EVs has gained significant momentum in recent years due to growing environmental concerns, stricter emissions regulation, and advancements in battery technology. As governments and industry push for cleaner transportation systems, EV adoption continues to rise. However, conventional plug-in charging methods present several limitations, including limited charging station availability, safety risk from exposed high-voltage connectors, and inefficient use of urban space. So wireless power transfer or WPT technology has emerged as a promising solution to these issues by allowing EVs to charge wirelessly through inductive coupling. WPT offers a safer, more user-friendly, and space-efficient alternative. Static WPT systems enable vehicles to charge when parked or stationary, while dynamic WPT systems take this concept further by allowing vehicles to charge while in motion. So as of October 2025, dynamic WPT is moving from pilots to early limited commercializations, mainly for fleets. On France A10 motorway, a live trial under normal traffic shows greater than 200 kilowatts average and greater than 300 kilowatts instantaneous power. Detroit has a public quarter-mile wireless charging street for tests and demos. Florida's SR516 is building about 1.2 kilometers, about 200 kilowatts for mixed vehicles. Sweden's Sommartorp Gotland 1.6 kilometers finished public road operation in 2023. Standards are catching up. SAEG 2954 for static is published. High-power dynamic G2954/2 is expected around late 2025 to early 2026. But our work focuses on the vehicle side hardware and power transfer stability rather than on building long road segments. We designed a DWPT prototype at 85 kHz using an LCC-C compensation network with a rectangular transmitter and square receiver to improve alignment tolerance and coupling uniformity during motion, and we studied receiver section spacing by measuring coupling match simulation closely. This complements industry pilots that target very high power, which are around 200 until 300 kilowatts for heavy vehicles. Next is conceptual and research methods. In the study, a square coil was chosen for the receiver due to its better alignment compatibility with the rectangular transmitter and improved coupling uniformity during motion. Its compact geometry also makes it suitable for installing on EVs. The transmitter uses a large rectangular coil embedded beneath the rod. This design reduces the effect of misalignment and power fluctuation when transitioning between transmitter coils during dynamic charging. The research also investigates the impact of distance between split receiver sections, testing different configurations to find an optimal layout. This helps ensure more consistent power transfer and system stability while the vehicle is in motion. So in short, coil shape and spacing help us keep stable charging while moving. So this is the circuit architecture. The system has these blocks, which are the full bridge inverter, LCC-C compensation, primary side, which is the transmitter, secondary side, which is the receiver, and lastly, full wave rectifier and filter. Next is the components calculations, which are the main parameters. So we are using the operating frequency 85 kilohertz, and the parameters are as shown. All right. So this also are the components calculation, but for the total inductance for two magnetically coupled coils. The value 1 is equal to L1 plus L2 plus 2M, and value 2 equals L1 plus L2 minus 2M, which is here the M is the mutual inductance, and this is also for 85 kilohertz. We use these relations in design and the simulation. Okay, this is the expected result from simulation, which is the ANSI simulation with a circular coil. This gives us a baseline to compare. Okay, next. Now we can see for our current experiment, also using ANSI simulation, which you can see there are transmitter and receivers shown here. The receiver now we are using is the square one. We compare fields and power transfer for this setup. We use this to judge improvements in our coil choice. Here we compare real-life coils and simulation coils. So in real life, the L1 equals 23. The L1 is equal 23.83 microhenry. L2 equals 5.84 microhenries. Coupling coefficient K equals 0.34. While in the simulation, L1 equals 32.41 microhenry, L2 equals 6.3 microhenry, K equals 0.38. So the coupling values are close, so we think that our model match quite well.
Now I show the basic structure. So the first one is the transmitter, which is a rectangle 30 centimeters by 10.5 centimeters with 10 turns. And for the receiver is circular 9.5 centimeters diameter. And this is the new one. This is the square receiver layout. The transmitter itself is rectangular, 30 by 10.5 centimeters and 10 turns. And for the receiver is square side 9 centimeters, 7 turns. So we also use the square receiver to improve alignment during the motion. So in dynamic tests, as the receiver moves across the road coils, the output power changes with position. The best power happens near the center positions, for example, around position 11 and position 29. So we start to move to the left to see how the So this is it. The maximum power transfer for the first point is at 12 centimeters, which is 4.30 watts. And also for the past experience is 1.8 watts. And then we go and move it to the left again, and it starts to reducing little by little. When we move away from the center, power drops because the coupling is a lot weaker rather than the one that is near the 2 points. So this is the second highest, which is 4.2 watts. This is the second point that is the highest power output, which is on 29 centimeters. And after that, we move to the left and it reduced again. So this is the expected results for the simulation for the past experiment. And the maximum simulation coupling K is equal to 0.34, which is quite similar. And for the next one is our current experiment. The simulation coefficient is 0.3811, and our real life coefficient, which is also quite similar, is 0.34. This is for the past experiment using the circular receiver coil. Our output power is the maximum is at 1.81, and the second one is at 2.3 watts. And the distance, it's the highest distance is about 12 centimeters and also 30 centimeters, we can see. And our past experiment shows a very little efficiency compared to now. So this is our latest data analysis. Position is at 11 centimeters and also 29 centimeters with the output power of 4.43 watts and 4.21 watts with the efficiency about 55% and 56%. And this is our circuit diagram. The first one, we have our full bridge inverter, and then connects to the LCC-C, CS1, L1, L2, and then full wave amplifier and the filter, and also the loop. So the design prototyping of a dynamic wireless pole transfer system operating at 85 kilohertz using an LCC compensation topology have been successfully demonstrated through both simulation and experimental stages. The transition from a circular to a square reciprocal coil, changing the diode into Schottky diode, and optimizing capacitor values have collectively improved system efficiency and reduced power loss, showing a higher power output compared to the past experiment. Based on the numerical and dynamic measurements, the output power reached a peak of approximately 4.4 watts, with performance trends matching simulation data, showing its higher power output at the midpoints, which is the positions of 11 and 29 centimeters. This indicates stronger magnetic coupling and better resonance alignment when the receiver coil is centered over the transmitter section. As the receiver moves away from these optimal points, the power gradually decreases due to reduced mutual inductance, confirming the system's sensitivity to coil alignment during the dynamic motion. The measured coupling coefficient K is equal to 0.34 until 0.38, showed consistency with theoretical expectations, confirming coil parameter estimation and resonance tuning with an error of 0.105%. So this is our reference. With that being said, thank you very much.